If you can share screen.
Okay, I'll share my screen.
Hi, Judy.
Hello. Okay. Can you see my screen?
Yes, thank you.
We've got it, Leslie.
Okay, I'll just put it on slideshow. Okay.
Yeah, that's perfect.
Okay, so today I'm going to chat to you a bit about space weather. That's my field. And I work at the University of KwaZulu-Natal in the School of Chemistry and Physics. But I'm not a lecturer per se. I'm paid to do research and promote space weather in the form of training postdoc students and postgrad students and postdocs. So it's actually my post is funded by SANSA, the South African National Space Agency. So here I have a picture of the South African Antarctic base called SANAE. We're in SANAE 64. We've been there 64 years, South Africa. And in the background of the base is a picture of the beautiful Aurora Australis. So this is the only visual representation of space weather. And you can tell by your senses, you actually would never know that the great danger it poses to our technology and modern society. It just looks really beautiful. So I hope in my talk I can kind of reveal this to you. And of course, it takes science to reveal this. We wouldn't know by our observation, just sheer observation. So basically, I'm going to try and answer three main questions. What exactly is space weather? How do we monitor it? Because we need to understand it, to prepare for it, and to mitigate its effects, just the same as atmospheric weather. And then I'll go into a bit more detail of the impacts it has on our modern society. But I tried to give this whole talk with not only a global perspective, but also a South African perspective, because we are quite involved in space weather in South Africa. You might not know it, but we are. So yeah, I'll try and also reveal that to you. So the first question, what is space weather? So space weather is defined as it describes the way in which the activity on the sun, so not just the sun is shining, whatever, it's the activity on the sun and the conditions in space more generally impact human activity and technology, both in space and on the ground. So on the left here, we have a graphic, obviously not done to scale. But here it's showing some characteristics about the sun. So when it's active. So basically, as you know, the sun is a fusion reactor and its surface is around 6,000 Kelvin. But its corona, the atmosphere around the sun, is about 1 million Kelvin. So that temperature allows the particles to have enough escape velocity to leave the sun. And that is what you're seeing here in this kind of red, which we call the solar wind. And the solar wind is more than just particles. It's also a magnetic field, because the magnetic field escapes with the particles from the sun. So in a plasma, so I don't know if you know what a plasma is, but we could say fourth state of matter. You know, you have a solid, you give it energy, and then you get liquid, you give it a bit more energy, you get a gas, and you give it a bit more energy, you get a plasma. Basically, enough energy to strip all the neutral molecules of their electrons. And so you've got ions and electrons. So that's a plasma. On Earth, they're rare, but like a candle flame is an example of a plasma. So in plasmas, basically, because they're highly conductive, if you place a magnetic field within a plasma, you can't separate the charges from the magnetic field, because if you try and move the charge, it'll create its own magnetic field, which will counter that force. So if you, in the previous slide here, you can actually see the Earth's magnetic field because the particles are actually tied to the field lines. So the field lines in the polar regions are more or less vertical. Okay, so you can see actually, in this picture, you can actually see the Earth's magnetic field. The only way you can actually see it with your eyes. It's in fact one of the reasons you are alive today, one of the major reasons that evolution happened on this planet. So, so getting back to the sun's activity, basically within the sun, which is a big ball of plasma, it is rotating, and because it is highly conductive, it produces its own magnetic field. And that magnetic field on the surface is rotating and convecting, and so it gets highly knotted. And that knotting of the magnetic field is what we call sunspots. And then when those knots release, energy can be released, and you see that as a solar flare. So that is some of the energy is converted to light energy. Now, many other forms of energy, the particles themselves get highly energized. So here I've got here, the sun sometimes produces bursts of electromagnetic radiation flares and highly energetic particles, solar energetic particles. And then the kind of the most exciting, like hurricane of space weather is the coronal mass ejection. And this is shown here where basically it is associated with flares, but you get this like big bubble of plasma breaking off. Okay. And then if it happens to be carried along by the solar wind towards the Earth, there's an encounter there, which I'll describe. And so this is the Earth here with its own magnetic field generated by currents underneath the Earth. And you can see that field is more or less a bit like in the shape of a dipole. So when you're at school, you probably were shown a bar magnet and then iron filings, and it's a very similar shape to that. So, and that more or less protects us from a lot of the solar wind's high energy particles, because as I described, particles are tied to a magnetic field. So to jump from one magnetic field to another is not possible unless you input a lot of energy. However, there are special circumstances where it is possible. And so therefore the magnetosphere is not a perfect barrier, but rather a leaky barrier. And when it's very leaky, we get storms, to be very kind of put it in a very layman's terms. So actually, just to put a little bit of context, the history of space weather goes back, way back, even though it wasn't called space weather then. But you know, people were always interested in aurora, fascinated. And as we had navigators going to the poles, they determined that, oh, this occurs in an oval around the poles. This is a map from 1860 showing you that the aurora occurs in an oval. And this is right up to date, one of the later images from the POES satellite showing you the auroral oval over the Antarctic. So we've been looking at the northern and southern lights for thousands of years. The other way we've been studying space weather in a roundabout way is learning to understand the Earth's magnetic field. So this really started with the development of the compass, the scientific understanding of the Earth's magnetic field. And then the other thing, sunspots relied on really the development of the telescope. And the data set for sunspots count is the longest scientific data set in the world, because we started counting sunspots in the 1600s. So, so there is a history to it, but bringing it also right up to date, our modern understanding. Here are three images. On the top here, we have the the Solar Dynamic Observatory, it's in a visual, and we see an active region here, sunspot region. And that sunspot region led to, here's an extreme UV image, led to one of the largest coronal mass ejections seen in the modern era. Well, I think it is the largest in the modern era, and it happened in 2012. And the reason we didn't have a catastrophe, a technological catastrophe on Earth, was it missed Earth. So we were lucky. But next time we might not be so lucky, and so we better be better prepared. And on the right here is an X-ray showing that how a lot of solar flares are strong in X-rays, X-ray emission. And you can also see how the spots, the sunspots, are often arranged in patterns. And this comes from, again, the rotation of that magnetic field causes the knotting to come in certain patterns. And those patterns repeat every 11 years. So there's this 11-year solar cycle where we get a maximum of solar activity, a lot more storms during maximum, but not necessarily always the biggest storms. Sometimes the biggest storms happen in the minimum, but we do get a lot less storms in the solar minimum. So a solar active region can lead to a solar flare, which can produce energetic particle flux, which is called a solar radiation storm when we do receive those energetic particles, or it can also produce a lot of X-ray flux, causing problems with our communication. So this interferes with our radio communication because it affects the ionosphere. The ionosphere is a charged layer above the neutral atmosphere. It's charged because, of course, sunlight can dissociate, can add in that energy to form a plasma. So, and they don't, it doesn't recombine back into a neutral atmosphere because above the neutral atmosphere, collisions are rare. Okay, so, or we can get this, the monster, the coronal mass ejection. And these can also produce highly energized particles. If the orientation of the magnetic field within that coronal mass ejection is what we call southward, I'll explain that a bit more later, we can get what you call a geomagnetic storm on Earth. So I'll just run through again the main effect. So if we get a radio blackout, that's mainly due to the X-ray emission from a flare. And that'll hit in 8 minutes because it takes 8 minutes for electromagnetic radiation to travel from the sun to the Earth. A radiation storm, which is highly energetic particles, can hit anything from a few minutes later because some of those particles are so energized, they're almost relativistic. So they're sort of like 93% of the speed of light. So they are coming, say, up to 12 minutes and after, but they can trickle in up to a few days. And if we get a geomagnetic storm, we monitor that with what we call indices, magnetic indices. So that's basically condensing how perturbed our field is on Earth by the solar wind. Okay, so it's condensing to one number, that perturbation, and that gives you a big idea of how big the geomagnetic storm is. And because the solar wind travels at an average of a couple of 100 kilometers a second, that takes a few days to hit from when a CME is launched on the sun to when we actually feel the effect on Earth. So as I said, the geomagnetic storm is the most kind of dramatic event. It's the one that actually produces the active aurora. And it's also a very complex phenomenon, so it's the least understood. And but all these types of solar weather can all occur kind of within one event, or you can just get one or two. It's not that you get one and or another. So just looking at kind of how often these occur to just give you an idea. So there's a very famous space weather event called the Carrington event. That's happened in 1859. And of course, it didn't really have much effect on Earth because there was not much technology then. So it wasn't like a big effect except the aurora. So there was an astronomer and he noticed a large region of sunspots on the sun. And then he noticed a few days later, there was a lot of auroral sightings. And these auroral sightings were even at very low latitudes, meaning that the geomagnetic storm was strong. So that event is like one of the big daddies. And a similar event happened again in about in the 60s, and then again in 2012. So in the 60s, it didn't happen in the 60s, in the 20s. And in those days, what did happen, we had telegraphs, and there were several fires at telegraph stations due to geomagnetically induced currents. So I'll explain what those are. But, and in 1989, we had a very, very large storm. And in fact, we had aurora in Durban in March 1989. I actually saw it. So believe it or not, we did have aurora. So how often would a Carrington-like event happen? Because if that happened, we would certainly have major disruption to our technology. Even today is where we have done a lot of preparations already, but yeah, there's still problems. So it's about a 12% probability in the next decade and about a 50% probability in the next half century. So in order to understand a geomagnetic storm, we've got to understand a little bit more about the Earth's magnetic field. So as I said to you, it's mainly a dipole field. It's called, the main field is the field that's generated basically by the molten iron in the outer core of the Earth. So that molten iron is highly conductive. It's rising to the surface and the Earth's spinning. So you're getting a spiraling conductor. And when you get a spiral conductor, like a solenoid, you can produce a dipole field. So more or less in a very simple terms. Of course, it's a lot more complex than that. And I'm not explaining it completely, but just to give you the kind of the flavor of why we have a dipole field. And that dipole field is inclined 11 degrees to the spin axis. And something you might not know is that the south magnetic pole is actually the north magnetic pole. It's highly confusing. But it was from naming conventions, etc., and they got it wrong. So when they realized that this was the case, they said, okay, we just call the north geomagnetic pole the south geomagnetic pole. So we do call it the south, but it's actually a north pole. And then further out into space, where you have had a quick glimpse of what we call the magnetosphere, which is the space governed by the Earth's magnetic field. Currents form from the interaction of the solar wind and the Earth's magnetic field. And those currents have their own magnetic field. So that further out where these currents are kind of happening, then the field becomes less and less dipole-like because they're modified by those current systems. So the magnetosphere is a very big place. You can see here there's a scale of Earth radii. So it can go to the sunward side sort of is about 10 Earth radii in front of us, but that tailwind of down the magnetosphere can go to hundreds of Earth radii. And the reason it kind of gets into this shape is because the solar wind, the main pressure generated by the solar wind is a ram pressure, so from its velocity. So it's blowing like truly like a wind. And the pressure here within the magnetosphere is generated mainly by the geomagnetic field that's got a much stronger field than the solar wind's magnetic field. So, so where those two balance, you get the shape in a windsock kind of shape. So you don't see the tail going out here, but it's in the shape of like a windsock. And this is a highly dynamic space. So if there wasn't for the magnetosphere, our atmosphere would be stripped away by the solar wind, but our magnetosphere gives us protection. In front here is a dashed line, which is the bow shock, and there's a shock wave because the solar wind is supersonic. So here's a little bit more of a detailed picture of the magnetosphere. And basically, you've got the sun on the left, and the solar wind's magnetic field are these white lines here. So say they are pointing downwards, as shown in this graphic. You can see with the Earth's magnetosphere, which is the North Pole is on the top, and we have the field lines coming out of the Earth, and they go upwards. So they are pointing up on the front. So if the solar wind magnetic field meets the Earth's magnetic field where they're oppositely directed, they can splice onto each other in a process called reconnection. This process is not fully understood yet, and we have sent satellites up to, it's been observed, and we do understand it in broad terms, but the bottom line of it is there are quantum effects involved because it happens on a very small scale. And there's still things to understand. But this is how the solar wind, the particles on the solar wind leak into the magnetosphere. And what's crucial here is you can see this line that manages to splice on, its footprint is down in the polar regions. And so this is why most of space weather basically manifests in polar regions, and that's why we go to polar regions to study it, because its most dramatic effects are there. And basically, on the left here, you've got the solar wind blowing, and so it has momentum where it pulls these lines going from here and backwards into the tail. Okay, so I will explain that in the next graphic, but I just want to point out that there's also, like, when you get charged particles trapped in magnetic fields, they get trapped according to the shape of the magnetic field and the way it's changing in space and in time. And so you get these radiation belts where high energy particles get trapped. And you have this plasma sheet where also high energy particles have got trapped. So just to explain this idea of what I call convection, basically, as these field lines move in from the solar wind and connect here, then starting 1, 2, 3, they're pushed back by the solar wind and they move into the magnetosphere like that. And then they will come and they will meet again and be oppositely directed again, much like they were oppositely directed on the front of the magnetosphere. Now they're oppositely directed in the horizontal plane at the back, and they can release again more energy, and then they snap. So much like you're releasing like a catapult, they snap, and that energy has to go somewhere, and it goes into the particles actually. So we can see, if we look at the foot of a field line here onto the polar region, you can see how it's pulled over the polar cap and snaps back and around to the front again. So there's this cyclical motion here. And so this is what we call convection. It's the movement of plasma in the polar ionosphere. And this is very crucial to understanding how much energy is being input, and we'll talk about that a bit later. So I just wanted to show you a little short video which really illustrates this process well and how you end up with the aurora with this process. That should be here. Okay. Just play this little video. So here we see like a little image of the sun with its active regions of the sunspots, and then say coronal mass ejection happens, and that is carried off with the solar wind. And then that can interact with the Earth's magnetosphere and open field lines, which are pushed back into the tail. Again, we get some reconnection at the back here, which energizes particles on those field lines. Those energetic particles can flow down onto the poles into the shape of the oval. So you can see that the reason aurora occurs in an oval is in fact because the Earth's magnetic field has the shape it has. That is why we actually have it occurring in an oval. So we go on to the second question now. How do we actually monitor space weather? So South Africa has a very top of the range, very modern space weather center. It was actually opened in 2022 in Hermanus. We did have a space weather center that was smaller, housed within the magnetic observatory before. So this has a history. It's not like we didn't have it and then 2022 we had it. But now we've got a really funky building that we have it in. And basically it's part of 22 regional space weather warning centers throughout the world. And basically we have weather forecasters sitting there 24/7 looking at screens like this. So basically looking at images from satellites of the sun and also looking at images of data on the ground and data from other satellites in the solar wind. Okay, then it's the job of the space weather forecaster to look at all this data, analyze it, and decide whether to give warnings and reports. Okay, so that's the kind of the major way that we monitor space weather. So of course, because it's so complex, it's actually very hard to forecast, much like atmospheric weather. It's so very hard to forecast. You know, you plan a day at the beach, you think it's going to be sunny, and then it rains. So okay, we can look at the sun and we can see effects, but as you heard from our previous explanation, some of these effects arrive rather quickly. And also the problem with the geomagnetic storm is it's not only just what leaves the sun, but you've got to track that CME to see if it is actually going to hit Earth. And you've got what you don't see is the magnetic field in the CME. That you require satellites within the solar wind to detect, which only really are effective to know the orientation of how effective it'll be towards the orientation of the Earth's magnetic field, also quite soon before it's going to hit. So basically, our most powerful tool is what we call nowcasting, where we're actually looking at real data all the time and sort of updating what's happening and then sending out alerts very, very quickly in order to mitigate, you know, further damage, because a lot of damage is often done in a cumulative way. So it's valuable still to give out warnings. So also from the ground, we do a lot of monitoring of space weather, and I'm just going to explain that mainly with a slant to South Africa so you can see what we're doing. So the first thing we can do to monitor space weather is to actually monitor the Earth's magnetic field, okay? So as I explained to you before, we do try and condense that down into indices, just a number that gives you like how perturbed the Earth's magnetic field is. So the KP index is an index that tells, basically it's a global index, so a number of stations throughout the world contribute to this index. And that's the index that really decides on what kind of alerts we're going to give. The DST index is particularly an index for geomagnetic storms, because basically it's only 4 stations in the mid-latitudes, Hermanus being one. And why they have to be in the mid-latitudes is they're trying to detect the influence of the ring current. So this is a current that runs in the radiation belts. And that current is so large during storms, there's so many particles being fed into there, that it generates a very big magnetic field, which quite strongly depresses the Earth's magnetic field because it's oppositely directed. And then there's the AE index, which is a more indicator of what's happening at the poles. Okay, that's another important index. But as far as South Africa goes, we have four major magnetometers in the Southern African region. It's SANAE, I think it's Mafeking, Hermanus, and Keetmanshoop, I think. Yeah, so these are mainly what they call flux gate magnetometers. So basically how a magnetometer works, it's much like a compass, but you're using a coil wrapped around a ferromagnetic material, just to enhance that. And you basically put a current through that. It generates its own magnetic field like a dipole field. And then if you switch that current like an AC in different directions, back and forth very quickly, the average field will be zero because the two fields are canceling out. They equal and opposite depending on which way you put the current. But if you put that magnetometer in the Earth's magnetic field, instead of canceling out to zero, it cancels out to an offset, and that offset is a measure of the Earth's magnetic field. But of course, the Earth's magnetic field has several components. So we usually divide it into X, which is geographic north, Y, geographic east, and Z, up and down. So what you can then do is place those coils at along each of those axes, so that you get the three components. However, of course, the Earth's magnetic field in itself, because it relies on currents under the Earth, is changing all the time. And therefore that what we call the declination, which is where the magnetic north is pointing. So you might have heard that the magnetic north pole is wandering all over the place. So that changes. So of course, then your flux gate magnetometers are often in the slightly wrong orientation. So the only absolute station is an Hermanus, and they have an instrument that accurately detects all the time that declination. But that's a much more complex instrument. So then you have to, from time to time, correct your flux gate magnetometers. The other thing we monitor is the ionosphere, this charged layer. It's not really above the atmosphere. It kind of overlaps the atmosphere. So during the day, when you have a lot of sunlight and more energy coming in, of course, you have a much bigger ionosphere, and it also divides into more layers. So it extends sort of round from about 80 kilometers right up to about 500 kilometers. And at night, it collapses more or less into one layer. So we need to monitor that because this is where space basically ends. That's where the magnetic field lines can cause currents to flow in this ionosphere, and these currents are very important. So basically, we have to monitor the currents in the ionosphere because they have their own magnetic field, which affects the Earth's magnetic field. And those currents can also lead to a lot of heating. We also need to measure the electron concentration, or thickness of the ionosphere. And that is definitely affected by solar weather, space weather, and cosmic rays. And we need to monitor the maximum usable frequency for radio communications. So, sorry, my dog's going a bit crazy, having a zoomie. Yeah, the instruments we do to do that is an ionosonde. Now, our ionosonde is something that transmits radio frequencies like in a variable ramp. So from certain, say, 10 to 40 megahertz, it goes through all those frequencies. And it's testing to see, it's a vertical instrument, points upwards, and it's testing to see when you receive the what frequency you will receive back, because that frequency is the maximum usable frequency. And it's related to what we call the electron plasma frequency, which is basically the electrons are much lighter than the protons. And whenever they're perturbed, they're the ones that shuffle around in this kind of oscillatory manner. And that's the electron plasma frequency. And in fact, it's those electrons that re-radiate the radiation back in order for us to receive it. So if your frequency is too high or above the plasma frequency, basically what happens is the electrons can't keep up and the radiation just pops through the top of the ionosphere and is lost into space. So we can't use it for over-the-horizon communication. So that's what our ionosondes do. We use GPS receivers a lot because GPS receivers can easily measure the electron concentration of the ionosphere, because the electron concentration is dependent on frequency and the time it takes for the radiation to get to the satellite and through the ionosphere to us. So if you use two different frequencies with the GPS, you can work out the electron concentration. Of course, we have the magnetic observatories, we have MT stations. Those are actually not only, they're also measuring the electric field of the Earth, because the Earth's electric field is important because of currents in the Earth. So, I mean, some rocks are more magnetic than others, or more conductive than others, and that's important to know. And we also have VLF receivers, and those receivers actually measure radiation that flows in ducts in the near magnetosphere. So it tells you something about the near magnetosphere. And so the other thing, and the last way we, and everybody throughout the world keeps an eye out for space weather is using satellites. In South Africa's case, we do have micro and nano satellites. And we do also use rockets and balloons. But we also, of course, buy time on the major satellites of other countries. So I just want to say a little bit about our space weather research in the Antarctic. So as I say, we started in 1960. SANAE 1 happened in 1960. And here's a picture of a man actually using a magnetometer, taking a measurement of the Earth's magnetic field then. And basically, we have more or less similar instruments as we have in South Africa, but added to that, we have the aurora. We also have some rheometers to measure radio noise, neutron monitors measuring cosmic rays. And the main thing we have there is the SuperDARN radar, which is used to measure it. You might understand radars bouncing off objects, but actually this radar is bouncing off like waves in the ionosphere of electrons. When electrons bunch up and down into kind of ripples, those ripples we can use radar to bounce off, and therefore we can start to understand the flow of what's happening in the polar ionosphere. So that's the experiment I'm mainly involved in. This is the radar here, and the antenna are between the poles. And these poles are about 15 meters tall. So and we have 17 of these poles because there are 16 antenna. So it's a big instrument. So just to tell you a little bit of SuperDARN, what we do is this is like a network of radars. It's a global collaboration, well, international collaboration. There's 9 countries, South Africa being the only emerging economy. Everybody's always shocked that South Africa is involved. when you go to any meetings, because it's all first world countries. But the reason we are involved actually is we had a very eminent space physicist here at UKZN, and he's sadly passed away, and he was my mentor, Dave Walker. And that's actually the reason why we're part of SuperDARN. And SuperDARN has done a lot of work in space weather, and is been cited and given awards by NASA and the Royal Astronomical Society. So here, this is a Southern Hemisphere bunch of them, and you can see the SANAE one there, and its field of view is like this kind of cake slice. They've all got these quite big field of views because they're over the horizon radars. They see long distances. So basically, they look into the polar ionosphere and they create one of their products. This is just one tiny bit of what we do, but it creates a space weather map. So it uses all the radars in each hemisphere. So it's created every 2 minutes. And this is the Antarctic. This is the Southern Hemisphere. And you see this flow that I described before over the pole, because these little vectors are all the radar measurements of velocity of the convection. So you see this flow over the pole and this reverse flow back. So on either side, they flow in opposite directions. And these flow lines are electrostatic potentials. So here is a point of lowest potential, and over here is a point of highest potential. Okay, so the difference in that potential here is being estimated at 52 kilovolts. So if you understand that the currents feeding this region at a time of a storm are around 10 to the 8 amps, the power being put into the ionosphere is similar to the power capacity, global power capacity. So if you added up all the power stations in the world, that would be something of that order. So this is a lot of energy coming to the polar region, and you can imagine how it dramatically affects the circulation throughout the globe, actually, because of that heating. And this map is really analogous to like a normal atmospheric map, where but instead of being governed by pressure and temperature and wind speed, here we're governed by electric magnetic fields and plasma motion. So it's a very similar thing. But this is just one product of SuperDARN. So finally, I'd like to answer the question, which is probably all the main crux of this talk, is why we study space weather.
The Bluetooth device is ready to pair.
And
the Bluetooth device is connected successfully.
So looking at this, maybe we start above here. We know that it affects our satellites. It affects their orbits. It affects their solar panels. It affects their electronics. And I'll talk about that a little bit more detail. Of course, energetic particles would affect an astronaut. If you're doing a spacewalk, you better watch the space weather. In addition, it affects aircraft avionics, especially the airlines flying at high altitudes. And it affects radiation doses, especially for polar routes. Sometimes aircraft are told to go lower in order to get more protection from the atmosphere. And also it affects, because it affects solar space weather affects GPS, of course it affects navigation. It also affects HF radar, radio communication. So transpolar flights, the GPS doesn't work on a transpolar flight. So they require for HF radio communications. And if that is not viable during the space weather storm, then they have to be rerouted. They can't fly over the pole. It's not safe. So they have to be rerouted, which costs the airline money. So SANSA actually provides every airline coming into the Southern Hemisphere with a space weather map. So the other thing, yeah, as I explained to you, because space weather affects the ionosphere and thickens it, it affects our communication with our satellites, especially GPS. It can be affected with errors as the ionosphere thickens, can also be disrupted. Okay, so I'll explain a little bit more about that. But because GPS is not only essential for navigation, it's also essential for timing. So on GPS, there are atomic clocks that broadcast time, and that timing is used for all financial transactions, stock exchanges, for many, many things. For also, like for mass transport systems, they need accurate GPS and accurate timing. So here you've got a train, which shows you how that's affected. And also when we get currents in the ionosphere, which generate their own magnetic field, that magnetic field can induce currents in power lines and cause transformers to blow. So higher voltages in these power lines can cause transformers to blow. Excuse me. So those are just some of the effects. So I'll just talk about a few of those effects in a bit more detail to give you a bit more of a flavor. So let's talk about the effect on satellite orbits. Okay, so satellites are generally either in low Earth orbit, medium Earth orbit, geostationary orbit, or high Earth orbit. So the low Earth orbit is extremely common and favored, popular, because it's cheaper and it's easier to communicate. But however, it is sensitive to space weather. So for instance, the space station has to every now and again put power on and boost their orbit because they keep basically sinking and coming to Earth. So any low Earth orbit satellite is constantly sinking, and especially if you get space weather, will sink a bit more. So if you don't have your own power on board, your satellite won't last very long, and you have to factor that in the lifetime of your satellite. So to highlight the dangers of space weather for orbits, in February 2022, SpaceX launched 49 Starlink internet satellites into a low Earth orbit. And on launch day, a CME hit the Earth. Now, they had been given warnings, but obviously Elon Musk didn't check. And so basically what happens there is because of the heating of the ionosphere that draws denser air from lower altitudes up. And so at that altitude, the air becomes thicker and the drag starts to get important. At the normal low Earth altitudes, this would not be catastrophic. It would lower the orbit. But on that day with Starlink, they first initially launched with a rocket to a kind of a midpoint, and then they used power within the satellites to get to their final orbit. So they were still in their kind of midpoint at about 210 kilometers. So they were severely affected, and they lost 38 out of the 49 satellites. And I have put a video there where you can watch them burning up. We don't really have time to watch that, but if you're interested. So the other way space weather affects satellites is radiation, of course. So there are many radiation effects on satellites. These include surface charging. So because you're bombarded with these high energy particles that kind of can penetrate the spacecraft, that ends up that the spacecraft gets at a different voltage to its surroundings and the plasma. And this can cause currents to flow on the spacecraft. Also, the different components might have different conductions or absorptions of these particles. And so there can be potential differences on the spacecraft and currents flow within that. There's also what they call deep dielectric charging. So basically, dielectrics are the material used for like breadboards where you put the electronics. And high energy particles can cause that dielectric to break down. And then you start getting conductors within that, which you don't want, obviously. And as everything becomes smaller and smaller, because they like to have the lightest satellite possible, these electronics are susceptible to single upset, event upsets. And of course, the space weather also affects the solar arrays by UV degradation. So this is an image of the total magnitude of the Earth's magnetic field. And you can see at the polar regions here, it's higher in pink, and polar regions about twice the magnitude it is at the equator. And then you can see there's this region of very low magnetic field called the South Atlantic anomaly. So it's just due to how the currents are moving around below the surface of the Earth. So, but that makes South Africa a very interesting place, because of course, when a satellite passes through this region, it gets exposed to a lot more radiation. And in fact, if you plot all these satellites, every time they have a single event upset, you definitely see the population, the occurrence of those single event upsets happen over almost all the time over the anomaly. So that's important. South Africa itself, because it's within the South Atlantic anomaly, hemolysis measured on average is about a 25% weaker than the average magnetic field throughout the world. And it's also the fastest changing in the world at the moment. It's lost about 20% of its magnitude in the last few decades. So this is all a natural phenomenon of the currents changing. We aren't due for a flip, but yeah, we don't obviously know quite when that will happen. So the other space weather effect is on communication. So the first way it affects our communication is HF radio communication. So of course we use HF to bounce off the ionosphere because it's refracted or bent by the ionosphere, and that depends on how, as I explained, how thick the ionosphere is, how many electrons are, and how they're moving around. And so this is very key because satellite communication is still quite expensive, even though Starlink now has made it somewhat cheap. It used to be very expensive. And so it's widely used still by planes, ships. Yeah, so it's an essential navigation. And that's mainly the X-ray flares are causing problems with the radio communication. And you can see here in X-ray, here's a solar maximum where you can see a lot more X-ray flares, solar minimum in the
so
solar
if I can
cycle,
just
a lot less.
can I just interrupt quickly? It's Gerald here. I had upgraded my Zoom during this meeting. I don't think the new unlimited has pulled through. If this stops, please.
I can hear you.
Okay, perfect. Okay, just to say a little bit more about the GNSS system, which consists of 28 medium Earth orbit satellites. Okay, so 4 always have to be visible. And they have onboard atomic clocks, as I said before, which continuously broadcast time. So from this, we can get a distance. And because we know the velocity of electromagnetic radiation, then by triangulation, we can get position. However, it's not the speed of light because the radio waves are, or the UHF is slowed by the ionosphere. It's called diffraction. It's slowing and bending of the signal. So that depends on the frequency of the signal, and it also depends on the properties of the medium, particularly in particular the electron concentration. So basically, what we do is we constantly are using a model which is updated by real-time data, and then that model constantly is fed to the GNS networks, and they can correct for those errors. Okay, so all the time this is happening behind your back. You don't realize it. And then also another thing is the radiation from us to the satellite, the receiver to the satellite, can also be affected, like broken down, what we call scintillation, where both in phase and amplitude, it's not smooth and can kind of we can miss signal. And so we have to mitigate that by designing within our GPS. So we often have what we call phase lock loops that lock on to the last bit of information they have for 10 seconds, etc. So that does also help with scintillation. So finally, just to give you a bit of idea of the products that, for instance, SANSA routinely supplies, because SANSA more and more has to live on its own funding, like make money. And although we are a government organization, but more and more encouraged to kind of find our own source of funding. So we sell these space weather warnings to telecom companies like MTN, for instance, because they need to know, to airlines. So every airline, as I say, that comes in the Southern Hemisphere gets a space weather map from SANSA, and that's to help them with potential problems with their communication, potential problems with radiation, potential problems with avionics. These things all have to be factored in. We also supply the warnings to banking for timing of their data and transactions, to power companies because of transformers blowing. I mean, even at our latitude, there is significant power loss due to solar storms. I think it's a couple of % a year. And also to mining companies, because mining companies do magnetic surveys and they need to know about how the Earth's magnetic field is being perturbed. We also sell the data to military, obviously, for their communications, and disaster management and agencies in the government. So just to also give you an idea of more or less kind of the problems with, I mean, the monetary consequences of space weather. In the US, insurance claims suggest that losses in their power grid from space weather are around about 5 to 10 billion US dollars a year. So it's not small change. And if we had to have a Carrington event now, the predicted cost just for the US would be around 3 trillion US dollars. So yeah, our modern society is pretty vulnerable. And all the time we are working behind the scenes to try and mitigate these effects and to also provide warnings to people. So I hope this talk has helped to understand space weather a bit better, and also to understand what we're doing in South Africa. And thanks for your time, and thanks for listening.
Sure. Thank you, Judy. Certainly something to look forward to. Chaos. The geomagnetic storm, you say it could take a couple of days to come to us. Does your monitoring sort of give a time frame? So for us common folk that aren't in banking and mining and in government, what is there potential for us to have some sort of warning? Can you say, okay, it's going to be here on Tuesday at round about such and such a time?
Yeah, so that depends on the solar wind speed. So usually the bigger the CME, the faster the speed, obviously. So anything from 2 to 5 days. And what happens is we do issue an alert at the moment we see a CME on the sun, a potential problem. It's like, but then of course, the chances are it's going to miss Earth, because Earth is like a small spot in the general scheme of things, you know. So so the trick is, number one is to start to track it as it moves to see if its path is possibly on a trajectory towards Earth. And the other trick, of course, is this whole magnetic field business. So that those kind of finer points in it make it more difficult to predict exactly what's going to happen. But the more knowledge we have all the time, the more we're getting better at predicting and knowing what's going to happen. But certainly we do issue warnings as soon as there is a CME on the sun.
And okay, assuming you're not in an airplane at the time it hits, in terms of if our computer is plugged in, or our cloud storage for our data, over and above it just being fried electrically, should we be sort of backing up our stuff? Would our external hard drives that aren't connected also be affected with that amount of electrical and magnetic coming in?
Not on the surface of the Earth. No, that wouldn't be a problem. Not on the surface of the Earth, but further up, yeah. So on satellites, electronics are a problem, yeah, but not on Earth.
Okay.
But it's just sensitivity to current flow surges, current surges, and yeah.
Okay, great, thanks. Anybody else got questions?
I have a comment.
Yeah.
Dr. Stephenson, that was absolutely fascinating, and thank you very, very much indeed.
Pleasure, thank you.
I second that as well. But Judy, I just wanted to know, how does it affect atmospheric weather?
So it does, in the sense that, as I described to you, the ionosphere and the atmosphere aren't separate layers, they like overlap each other. So they actually affect each other. So as the ionosphere heats up, so it passes on via collisions some heat to the atmosphere. So the whole circulation pattern of the Earth, the whole climate of the Earth is sensitive to space weather, definitely. So there is, so you notice during a big solar storm, there will be a change in circulation. You can even get, because mostly the hottest place on Earth is the equator and the coldest place at the poles, mostly you've got a circulation pattern that goes out of the equator, up, over and down, sinks into the poles. But when you have a solar storm where a lot of heat is being inputted into the poles, you can have a reverse circulation towards the equator even. So you can see how that whole circulation pattern can be modified. But it happens in quite a predictable way. We factor that in our models. So if you're going towards, is it like something to do with climate change? No, that's already factored into our models. We understand where in the solar cycles we are and et cetera, et cetera. So that's all been factored in.
That not only the
Yeah, Mike, you went on to mute there.
Sorry, I was unmuted there. So is that not, you said 11-year cycle that you have with solar spots and that sort of thing? Is that not why we sort of have cyclical weather here in our atmosphere?
There is cyclical weather, yes, from the solar cycle, yes. Yeah,
Okay.
there is, and it's certainly, as I said, it is an effect, and yes, there is that cyclical pattern. But as I said, it's not something that's causing the long-term heating of the atmosphere. That's a much bigger trend on top of that. You know, this is like a smaller cycle, and that's a much bigger trend on top. But maybe I shouldn't have mentioned climate change, rather just keep it simple. Yes, it is affected by the solar cycle.
I'm a geologist, so I do understand cycles and all of that sort of thing. So I was just looking at it in a short term that we are, the time that we are here.
Yeah.
On Earth. You know, I know that it's not going to affect the long-term solar heating or the climate change that we've got.
Yeah. It's a variation. It's up and down. Yeah.
Any other questions?
Not so much a question, but a comment. I just wanted to say from Joburg, ASSA Joburg, thank you so much. That was a really, really fascinating talk. I like that you went more into the physics side, because I'm currently studying physics. So it's nice to see it's nice to see electromagnetism like in real life, in a real life situation. So yeah, thank you so much.
Thank you. Thanks for your appreciation.
Judy, same here. Thanks very much. Really fascinating.
Thanks, Sorrel.
Anybody else? Going once, going twice.